Hello everyone, I'm Giuseppe Vitto and this talk will be about automating truncation of differential trails and trail clustering in ARX, a joint work with Alex, Lewin, Daniel and Wesley. Let's start with some preliminaries. We denote by XDP the differential probability of addition, that is, the probability with which the n bits inputs XOR difference alpha and beta propagate to the n bits output XOR difference gamma through modular addition. This probability is not zero if the Lippmann-Moriarty condition is satisfied. This condition requires that the XOR of the three differences alpha, beta and gamma at position I is equal to the value at position I-1 of alpha for I greater than 0, while is equal to 0 at the least significant bit. For example, we can here see 2 bit positions at which the condition is satisfied, including the least significant bit, and 1 bit position that violates such condition, the last one, and makes the XDP probability equal to 0. Lippmann and Moriarty not only provided a sufficient condition to have valid transition through differential modular addition, but they further provided a closed formula for computing it. Starting from their condition, such probability can be computed counting the number of bit position I at which alpha I-1, beta I-1 and gamma I-1 are not equal, excluding the most significant bit. What they show is that for each such position I, the probability drops by 1/2. Of interest for this talk are truncations for the differences alpha, beta and gamma involved in a modular addition operation. Computing a truncation informally requires to identify some of their bits so that by varying their assignments according to some constraints, we always obtain transitions with non-zero XDP probability. Aiming at this, we introduce some notation. We denote fixed bits that can either be 0 or 1 with a dot, while we use a star to indicate truncated bits. In this context, we'll often call such truncated bits free bits, since they can take with equal probability either 0 or 1. As we can see in this example, we have an input bit value equal to 1000 that we decide to truncate in its second rightmost position. Since other bits remain fixed, its truncated representation will then consist of 2 dots, 1 star and another dot. This representation in turn corresponds to 2 non-truncated values, one for each assignment of the free bit, namely 1000 and 1010. In our paper, we detail 2 lists of rules to truncate differences, namely simple and relaxed rules, so that truncation made according to them satisfy Lippmann-Moriarty condition for any valid assignment of the truncated bits. We start providing an overview of simple rules, which we named in this way since are easy to implement and do not require to keep track of complicated dependencies among truncated bits. In our first simple rule, we require that at most one truncation exists per bit position, while we allow no truncation in the least significant bit. In this example, we can see 2 bit positions that conform to this rule, and 1 bit position that instead violates it. The rationale behind this rule is that by allowing more than 1 star bit per bit position, we increase the number of truncated bits propagated, which in turn result in complex dependencies to satisfy to guarantee validity of Lippmann-Moriarty condition. This condition is indeed the reason why we don't allow any truncation in the least significant bit. The second simple rule concerns the XOR operation. In this rule, we require that there is at most one truncation by bit position for the differences entering a XOR operation. In this example, we see that for 2-bit positions, the rule is satisfied, but is then invalidated at the position where we have red crosses. In fact, when at most one input to XOR is a truncated bit, then the output is either fully fixed or linearly, depends on the other input bit. The rationale behind such rule is to again maintain simple dependencies among truncated bits. Our third simple rule is the following. If at position i-1 at least 2 bits are fixed and equal, then all bits at position I must be fixed. This rule, motivated by an impossibility condition of Lippmann-Moriai, ensures that we do not truncate a non-zero probability differential addition transition into a truncation which has some of its non-truncated differences of probability 0. An equally important consequence of this rule is that it allows for linear time computation of the exact probability of a truncated trail, which we will show next. In order to discuss how we can compute truncated trails probability, we introduce some definition. The first one is simply a restatement of Lippmann-Moriai's algorithm for computing XDP expressed at the bit level in terms of conditional probabilities. Here, Pi of j denotes the conditional probability of the differences alpha, beta, gamma at round j and bit position I, conditioned on the difference bits at previous bit position alpha, beta, gamma, j, i-1. The second definition instead expresses the conditional probability P0j of the difference at the least significant bit of round j, and as it refers to the least significant bit, this probability is not conditioned on any previous bit. It is then straightforward to generalize this definition of differential probabilities for bit entries to compute the probability of a non-truncated trail. These, in fact, simply correspond to the product of all bit conditional probabilities. It follows that while computing the probability of a trail, we can compute each individual Pi of j independently. Simple rules allows us to have a linear time algorithm for computing the probability of a truncated trail. Its main idea consists in computing the products of all conditional probabilities which are conditioned on bits containing a truncated bits. Suppose we have a certain truncated bit at round k and bit position r-1 which propagates through additions and XORs to some other bits. It follows that when the first bit is assigned to either 0 or 1, the subsequent assignments for the dependent bits will give rise to two non-truncated differences with associated conditional probability PRK0 and PRK1. We then just sum these two probabilities and multiply the result to the remaining bit-by-bit probabilities not conditioned on truncated bits to finally obtain the probability of the trail. To better understand how this algorithm works in practice, we illustrate it with an example. We compute the probability of a truncated trail on 3 rounds containing 6 truncated bits. Note that of these 6 truncated bits, only 4 are independent, as signified by the 4 colors red, green, blue, and orange. In order to compute the total probability of this trail, we first compute the sum of the products of the deconditional probabilities of bits that are conditioned on the red truncated bit, that is P10(0). Similarly, we compute the sum of the product of probabilities for green, blue, and orange truncated bits as well. We then multiply the product of these probabilities by all remaining condition probabilities that are not conditioned on any truncated bit. The result is the differential probability of the truncated trail tau, which is the sum of the probabilities of all non-truncated trails encoded in its truncated representation. There is, however, a caveat while computing the probability of a truncated trail. Truncations might have overlaps when expanded to non-truncated trails. To address this, in our paper we propose an algorithm that, for an input non-truncated trail, produces a set of non-overlapping truncated trails. Here, instead, we describe an analogous algorithm which addresses a simple problem, namely merging a given fixed truncated modular addition differential A with another distinct differential alpha. The full trail merging algorithm is based on the same idea and addresses three possible relations that might exist between A and alpha in terms of sets of non-truncated differentials. In particular, A and alpha can either be disjoint, subsets, or partially overlapping, as explained on the slide, where also a small for beta example is provided. For such A and alpha, the merging algorithm makes a decision depending on the relation which exists between them. More precisely, if A and alpha are disjoint, it then outputs the set consisting of A and alpha. If instead alpha is contained in A, then it outputs simply A. Finally, if A and alpha are partially overlapping, then the algorithm splits alpha into two parts, alpha prime that is disjoint from A and alpha second that is contained in A. It then outputs the set A and alpha prime. We note that once a differential trail is added to the set, it cannot be modified further to keep their non-overlapping property preserved. Therefore, only the input differential trail can be modified, that is alpha, but not A. In practice, the full trail merging algorithm works analogously to this simple example we just illustrated. We then applied all these tools to the block cipher spec 64. Here, we are interested in finding the best distinguisher we could, consisting in a set of unique output differences so that the logarithm of the signal-to-noise ratio is greater than 0. By applying simple truncation rules on an optimal weight 15 round trail, we obtain a set of 15 non-overlapping truncated trails, which expand to 112 non-truncated trails, 22 of which have probability greater than 2 to the minus 64. We can then make a distinguisher of these 22 trails with overall accumulated probability equal to 2 to the minus 5905 and signal to noise greater than 0.49. Aiming at computing more truncations, previous rules can be relaxed in a way that Lippmann-Maria condition is satisfied automatically. We achieve that by introducing dependent truncated bits that we here represent with a tilde star. These new bits generalize free star bits since their value depends in more complicated ways on previous, truncated or not, bit assignments. In practice, such dependencies are enforced by modeling their value with a nonlinear multivariate Boolean function. In relaxed rules, we kept one rule from the simple ones, namely that we allow at most one truncation per bit position. The reason is the same, that is, we want to keep truncation fast. Our first new rule concerns the XOR function. It allows the XOR between any truncated bits, as opposed to the corresponding simple rule where we allow only one of the inputs of the XOR function to be a truncated bit. The rationale behind this rule is that the XOR function only introduces linear dependencies between truncated bits, and as we are representing every truncated bit with a Boolean function, such linear relationships are easy to keep track of. Our second new rule concerns the modular addition. It describes the circumstances where the truncation can freely happen without invalidating the hypermemory condition. Namely, if at both bit position I and I-1 two bits are fixed and not equal, then we can freely truncate the remaining third bit at position I. Since such truncation is independent from previous ones, we can use a normal start bit to represent it. The rationale behind this rule is simple. Let us think back on the hypermemory condition for bit I. If the bits are not equal at position I-1, the XOR in the condition is not restricted. Thus, if at both positions I-1 and I two bits are fixed and not equal, the third bit at position I can be any values, as that value will not create any conflict. Our final relaxed rule also concerns the modular addition. If at position I-1 two bits are fixed and equal while the third is truncated, then at position I we allow truncation of gamma I as a dependent bit till the star. To elaborate on this rule, let us show an example for its use case. Here, at bit position I-1, alpha and beta are equal, while gamma is truncated. Then we can set gamma I to be equal to the values taken by a Boolean function, which is modeled according to the relation reported in the slide, and where the simple start bit is modeled with a new independent variable into the underlying ring. The rationale behind this rule is that if we define our new truncated bit using this methodology, then gamma I depends on bits at position I-1 in a way that hypermemory conditions are always satisfied. We note that this rule might introduce highly nonlinear dependencies among truncated bits. Clearly, there are advantages and disadvantages of using relaxed rules when compared to the simple rules. To name some, we have that relaxed rules return a strictly bigger set of truncation than simple rules. Computing truncations remains in most cases fast, and we can catch a significantly larger portion of the available signal. On the other hand, there are some drawbacks to these rules, namely, there is no simple merging of truncations, the sets of non-truncated traits arising from different truncations might not be disjoint, and computing the weight of a truncation requires an exponential number of operations in the number of dependent truncated bits. We now move our focus back to Spec 64. Other than truncations, we investigated other techniques to build distinguishers. One approach we detailed is to start from an optimal weight trail and split it into n plus k rounds. By iteratively increasing k, we then compute the differential effect of the first n rounds, while maximizing the signal noise from freely varying the last k rounds. Since computing the differential probability over more than 10 rounds quickly becomes prohibitive, we further split the first n rounds into two chunks of j and n minus j rounds, so that the sum of the differential probability is minimum. To be able to compute such differential effect, we used SMT solvers, and the best 15-round distinguisher we obtained was by starting from an optimal weight trail and using parameters k equal 3, n equal 12, and j equal 3. Such distinguisher consists of 389 unique input-output difference pairs with overall probability close to 2 to the minus 55. Another question that might then arise is, what if we build distinguishers similarly as before, starting from non-optimal weight trails instead? The answer is that in some cases, the corresponding distinguisher results better in terms of accumulated probability and signal-to-noise ratio. In this example for 11 rounds trails, we can indeed see marked in Rhine the distinguisher built starting from an optimal minus 42 weight trail, to which we include more and more trails by varying bottom rounds. Interestingly, by starting from suboptimal traits instead, we observed that the corresponding distinguishers beat the red optimal one in terms of accumulated probability at multiple signal-to-noise ratio levels. To conclude, we described a new tool for the automated truncation of differential traits in ARX cipher. The tool generates all possible truncation up to certain predefined rules of an input non-truncated trail and outputs a set of truncated trails with associated probability. We discussed two different sets of truncation rules, the simple and relaxed rules, which allow different trade-offs in terms of signal code, compact margin of truncation, and truncated trace weight computation complexity. We use our tool on the block surface spec 64 to build distinguishers requiring lower data complexity than the one based on the best non-truncated differential. And we investigated distinguishers built from suboptimal weight trails and showed that in some cases they are better in terms of probability and data complexity. Thank you.